We're at a point in the semester where we can tie together many of the concepts that we've been studying up till now to a topic that I think is of great interest to many of you. It's the subject of how drug molecules work, and when we understand that this is really an aspect that's rooted in enzyme mechanism and inhibition, it'll become clear that there's really nothing magical about these molecules, but their behavior can be understood using the science of bioorganic chemistry. In setting out to think about how drug molecules work, the key questions that we need to address, and the questions that we're going to be addressing in this webcast and the upcoming webcasts really, are illustrated for you here. We need to stop and think about what are the biological targets of interest. What molecules, what proteins, for example, might we want to interfere with in order to achieve selective toxicity, or what proteins might we want to inhibit in order to correct some diseased state. Once we know those targets, we need to think about what are the normal molecular mechanisms by which these targets carry out their action, and then we can think about how to do the molecular engineering side of the problem, that is, how to design a drug that could interfere with this mechanism. So as you think about what's going to be coming down the next few webcasts, these are the questions that I want you to think about. What's the target, what's the mechanism, and how can we interfere with that mechanism? Before we get started to deal with that, let's just take a quick peek at some of the drug molecules that are out there and of interest. At this point in your career in organic chemistry, you have a very good understanding. In fact, your understanding of organic chemistry today may be better than it will be the rest of your life. And so let's take a look at the organic molecules that are used in therapeutic applications. You can download this file, and it's going to be a high-resolution PDF file that has the top 200 generic drugs that were sold in 2007. And so I would encourage you to take a look at this, and with your knowledge of organic chemistry, just go through some of these fascinating structures, looking at what they do, and checking out some of the chemistry behind them. For example, are they heteroaromatics, or how many of them are aromatics? What kind of functional groups are present? And what about stereochemistry? Is that important or not? You'll begin to recognize some of these drug molecules, and others you may not recognize, but I suspect that many of you will be prescribing these drug molecules or something close to it, or some advances that will be coming down the pipeline in the future. So what's our first target? Well, it turns out that a class of enzymes known as protease enzymes are very useful as drug targets. We've already encountered one type of protease enzyme, that's the metalloprotease enzyme, but there are three others of interest. And so in the upcoming webcasts, we'll be taking a look at the serine proteases, we'll be looking at the cysteine proteases, and we'll have specific examples, sort of the prototype serine and cysteine proteases, chymotrypsin and papain. Then we'll be looking later on at the aspartyl proteases, which are important for inhibiting and correcting the virus HIV-1. So let's take a reminder of what it is that a protease is and how it's able to achieve its mechanism of activity. Its mechanism of activity comes about because it's able to hydrolyze the peptide bond. And so in this substrate, there are two possible peptide bonds. The addition of water across the left one gives the products that are shown over here. They're amino groups and carboxylic acids. If we hydrolyze the peptide bond over here, which is similar but slightly different, we'll again get a carboxylic acid and an amino group. The rate constant, K1 and K2, this is going to illustrate just how remarkable protease enzymes are. K1 and K2 have incredibly small numbers, 10 to the minus 11th per second, in the absence of a protease enzyme. So at 37 degrees, a neutral pH, basically it would take 250 years to digest or to break down that peptide bond to 50% of its initial concentration. So if you were thinking about meat digestion, which is where really some of the initial proteases evolved from, it would basically be a long time to get that piece of meat dissolved.